So the common coin is kind of the normal way to do this. That's what everyone in the literature used to do. But yeah, like Bart was saying, it's really not that easy and it has problems. But we're lucky because Silvio Micali came up with a paper called Byzantine Agreement Made Trivial while we were researching this. And this gives a very elegant way to not require a common coin. So instead of having a magical number that appears in the sky that's unpredictable and that everyone can see at the same time, so it's common and unpredictable, we only require a weaker kind of magical device, which is a random binary value that appears in the sky that frequently, so say more than 50% of the times, more than 20% of the times, whatever, more than 90%, as long as as long as it happens at a predetermined frequency, or you can put a lower bound on the frequency, it will then be common and unpredictable. But sometimes it will just be junk, and everyone will see something different. So Silvio Micali, in his paper, explains how you can replace a common coin by a device like this that's easier to obtain. And so I'll first describe how to do this. So that's basically explaining Silvio Micali's paper. And then I'll describe how we have a concrete coin. So how to do this? Instead of flipping a coin to decide when you see a supermajority of auxiliary values, you'll do it in 3 steps. First step, so you consider it's like you had flipped a coin and it had given true. So it's entirely predictable, but it's definitely common because everyone follows the same rules. So when you see a supermajority, if they're all true, then you decide true and you move on. If they're not, you estimate false and you move on. Second step, you estimate false always. So it's also common, but also predictable. If you only did these two, if you only did true, false every now and then, then that would possibly be gameable because you need a source of unpredictable randomness. So that's why you add a third step where you use your magical device that sometimes is common and unpredictable. It's always unpredictable, but sometimes common. And then you never decide. You only, if you see a supermajority that agrees with the flip, then you estimate this for the next round. And what that does is it nudges everyone at some point to be in agreement on the estimates. But if they're in agreement on the estimates, then with the binary value gossip, whatever malicious input is offered trying to counteract this agreement is going to fail because binary value gossip will filter malicious values. So that's the process in a nutshell. I hope you followed me. So the way we do it, it's not leader-based, because if you were leader-based, you wouldn't be permissionless. But let's assume there was a gradient leadership that's always different. So you would be able to say, for instance, alphabetical. Alice is better than Bob, which is better than Carol, which is better than Dave, for this time. And this always changes. It changes for each meta-election, for each consensus decision. So you just say you're able to pick an order. And that's random. So then what you can do is that you can use that for being common with a certain probability. Because if you pick a node randomly in everyone, you've got 2 chances out of 3 that are honest. And you've got a high probability that they're honest and that they're going to be responsive within certain limits. And that's why we've got some synchrony. But so you need 2 things. You need a way to rank nodes and a way to assess, say, to wait for them for a certain duration, but it's not time per se, but say wait for them for a while, and if they're not responsive, then just pick the next best leader, like assume that they're faulty or something like this. So if you can do this, you can use the most leader or whoever is the most leader responsive node as a source of commonality, and then you can use as a source of unpredictability, pick a gossip event that they generate after a certain point so that you know that no one is able to deduce the hash of this gossip event, for instance, before it happens. So that way you get common and unpredictable. So you say, I predetermine that I'll pick Alice, and I'll wait for her to say, receive something that's after her auxiliary values, so that before the auxiliary values you can't predict it. And then I'll take this gossip event and extract a binary value from it, say least significant digit, because this happens to be random. So the two problems we have to solve for this is order and assessing responsiveness. Because if at some point Alice doesn't respond after a while, we just need to drop it and pick whatever. We could even pick an actual random number, it doesn't matter. We don't need to be common in that case. So to obtain the gradient leadership, the ranking of the nodes that's different at any time, well, that's what we always do to get kind of random stuff. We use hashes. So we sort the nodes in terms of their XOR distance between their own public identifier and what we call the round hash. So the round hash is just something that's constructed so that it's different all the time. So it's the hash of identifier of the subject of the metavote concatenated with the hash of the latest consensus gossip event concatenated with the round numbers hash. So what this does is it makes it unique to any meta election. So yeah, it's very trivial. So if you just do this XOR sorting, then you've got your rank, and there is no magic in this. There is no synchrony assumption. That's completely trivial. No, this slide is the slide where we're not quite happy with what we've got at the moment. So to establish responsiveness, it's better than, say, waiting 10 minutes, because that's completely synchronous, that's completely garbage. But we just say we define a pattern of gossiping where some messages we send are a request and some messages are a response. So every time I send a request to a node, if they're honest, they will answer to me directly with a response. So it's not pure gossip where you just pick people randomly. You pick people randomly, but also if you receive a request, you have to follow it up with a response. And then requests are sent periodically, so that's like normal gossip. So there is normal gossip happening at the request level, but when you receive a request, you must respond. That's how it goes. And then, instead of waiting for, say, 10 minutes, which is synchronous, we say you wait for responsiveness threshold responses to come back to our request after the time at which you decided to, say, have a timer and wait for a little while. So what you want is to give Alice, assuming if she was honest, give her the time to come back to you. So you say, for instance, I'm going to take 10 times n log n, or whatever, n log n, because that's the typical speed at which information progresses through gossip. So you do a constant times this, and you say, if Alice was honest and wasn't slower than, or like wasn't 10 times slower than average, that's where there is a synchrony assumption. So if you say, if Alice was not 10 times slower than average, then I'll consider her event that didn't exist before, and I'll use that as my source of random. And so every time you pick someone that's sufficiently responsive and honest, which will happen probabilistically often, then you're good, you've got your source of random. So that's how we devise the concrete coin to then use Michaelis' algorithm that I described before. And so this is really how things are done. So yeah, as I've told you, that's where our synchrony assumption lies. So handing back to Bart to come back to the properties we ended up obtaining.